пора начинать. Начинаю, да? Okay. So, at the end of the previous lecture, I started geometric realizations of simplicial sets, and the formula that I used to define this was the following. So, suppose I have X, just some simplicial set. Then the geometric realization was defined as a tensor product of functors X and the functor that I call top. Recall that the delta top was the simplicial object in the category of topological spaces. And when you have one functor which is contravariant, another functor which is covariant, you can form a tensor product. And of course, the special case would be a tensor product of a left module and the right module. So, have you seen tensor products before, functors? Well, I wanted to add some details how to work with this. Maybe I started the definition. So, what I'm going to say next, this is just kind of a remark about general category theory. So, suppose you have the following situation. Well, let me define this a little bit more generally. So, more in general, and this is not the most general situation, but still sufficiently general. So, I assume that I have a bifunctor. So, in general, if we're given a bifunctor, which I'm going to call tensor product, but that's a different tensor product. So this will be from the V cross M to the M. So where V and M are just some categories, right? And the right way to think about this is if you know something about the enriched categories, then this is the M is enriched over V and it tensored, meaning that you have a notion of a tensor product of an object in V and object in M. So, like for example, the category of simplicial sets itself, if it's not just a category, right, you can form a simplicial set which is a mapping space in this category, and this category will be enriched over simplicial sets. But at the moment, you can just take a functor. So then you can define, let me say that you have two functors. You have a functor f, which is some covariant functor from some category M, which we assume that is small, and functor G from the category D, which is small, to the category M, G from the opposite category. So D is a small category, as we usually assume for the diagrams. Right, so then you can, a simple definition will be something like this: tensor product of the G and F over D. Well, this is the so-called coend. Well, a long formula will be something like this. Just a second, I think there's some not exactly right. So this G is with values in the V, not M. So then this will be the formula for the tensor product. So I reduce this to the notion of a coend, but coend also can be reduced to something that we understand much better. So this coend is isomorphic. So this is definition. Yeah, and short notation for this will be something like this thing, to avoid writing arguments. And this is defined as a co-equalizer. Well, not defined, but you can give a definition of a coend of any bifunctor in terms of their natural transformations. But important theorem about coends is that you have a formula for the coend in some sense like a formula for any colimit. Right, any colimit can be reduced to the coproducts and coequalizers, and this is the case for the coends. So these two maps are the obvious maps that you have in this situation. Right. So, for example, if you look at this map, well, you can, since this G is contravariant, right, and the map is from the D to D prime, when you apply this, when you apply G to the F, you'll get a map from the D from the D prime to the D, and so you'll get one map. Well, I'm writing this D, but for one map you'll get D, for other map you'll get D prime, but it's convenient to write G just for all the arguments.
So the upper map is going GD prime goes to GD, and the lower map FT goes.
Yes, yes. So this is just map induced by this by functor. Yeah. So that's how you can think about this particular coend. Well, just for the completeness and to avoid mistakes, I also want to write a general formula for the. So more generally.
Shouldn't there on the right much be FT prime? Or it's just FT?
No, for depending on which map you apply, as I said, you'll get the answer here D or D prime, but they coincide. So I can use in this kind of in a variable, or which I take the coproduct, I can use any letter that I want. For example, I can use something like little p, but usually in the text, when you see such formula, the letter here is D. Yeah. So more generally, you can say that you have the following. You have a, say, bifunctor H from some category. No, I call this D, so let this be D op cross D to some other category M. Now this is not important, there will be no tensor product, just some category. And then you can write a formula for the general coend, say over D, H. So this will be, well, again, this is not a definition, the definition in terms of some universal property, but really when you do some computations, you need the formula, not just a definition. So, and this is just a straight, you can see that this is formula of the same nature. I missed the coproduct. Instead of using this tensor product and two functors, I just assume that they have a bifunctor of the right nature. So this is coproduct over all the f's as before. Sorry, this is D prime and D. And f is from the D to D prime as before. There are two maps as before, and this is to the coproduct over D, H, D, D. So of course this is kind of very brief. You can read about details about these coends and coends. Of course, for the end, the formula will be dualized. Instead of the coproducts, you'll get products. Maps will be in the other direction, and here you take equalizer. Yeah. So this is very brief, but you can find details in any reasonable textbook on category theory. You can learn it quite quickly. I think it's very easy material. So here we just use this kind of to give a definition, and we want this definition to be very short. For example, why I like this definition? Well, because you can see, well, if you ignore this part about coequalizer, you can say that this tensor product, sorry, about the coend, you can say this is tensor product is just this thing. And this is a colimit, kind of special kind of a colimit. And since colimits commute with colimits, you can immediately see that this thing commutes with colimits in both variables, which follows immediately just from the definition as a tensor product. Okay, just a remark about the, in general, what's a tensor product. And in this particular case, let me maybe rewrite this one more time. So I can say that the, unfortunately this is quite short for the formula, but okay, I'll try it. So geometric realization, maybe I'll write it here. The geometric realization to be to give you an explicit formula, this is coequalizer. So you take a coproduct over all the maps. Now, using my notation in the category delta, this is from the m in brackets to the n in brackets. I have xn product with the delta m top, two maps, coproduct over m, xm delta xm top. So in this case, the tensor product that I have in general formula becomes just a Cartesian product, right? You can multiply, you know how to multiply a topological space by a set. You just take as many copies of this topological space as you have 2 points, or you can say that you have discrete topology on this, and this is the product in the top. And even more concretely, I can continue this formula and give you still correct, but more approachable and in some sense more naive definition. So if you want a geometric realization, you take a coproduct over xn product with the delta n top. Well, I'm just kind of writing what's an equalizer is. Equalizer is some kind of quotient, right? So modular, so this topological space modular some equivalence relation. And this equivalence relation looks as follows. So I have f star applied to x t. So this is kind of point in this product. And this is equivalent to the x f lower star applied to t. So here, as usual, well, t has to be, sorry, x has to be in the, x has to be in the xn, and t has to be in the delta n top, and f here is just, well, can be called cost-simplicial operator. So sometimes people avoid talking about this. Well, you see, to work with this kind of, you need to know some category theory, which in particular I can never cover in my introductory class in category theory because I don't have enough time. But you can reduce this also to this very explicit thing, what geometric realization is.
Isn't lower x should be in xn?
Here?
Yeah.
This is xn.
It's n?
N, everything is n. Because I take this thing, I just switch from m here to the n, right? And this co-equalizer gives me an equivalence relation. Oh, I can as well write m everywhere, but
Yeah, but f alpha of x, comma t is lies in what? In xm times delta n?
no. When you have x here.
Yeah.
Yeah, here, yes. I think it makes sense. Yes, this is m. Yes, thank you.
Or
Oh,
delta. Suppose delta.
yeah, yeah. Oh, like this.
No, I suppose if you
No, I need to switch them. This is m, and this is n. Yeah, and this is maybe also m, right? To get exactly formula like this one. Okay.
then you should have xn and
Yes.
delta n.
Yes. Okay. 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 Okay, so maybe I'll just write this, what I said in the words on the blackboard, that you have the property, or for example, if you consider a colimit, say, returning to the general situation, so colimit of the ji, and then you take a tensor product with f, you can commute them and write this. This is the same thing, so this isomorphic to the colimit ji tensor f, right? Again, just colimits because colimits commute with colimits, and tensor product is a sort of colimit. And they will be also true for the second argument, but here I can use something that we already know as any presheaf. The simplicial set is a colimit of the kind of representable presheafs, and representable presheafs in this case we call the standard simplices delta n. So say this is colimit over the elements of the simplicial set X. Right? And then we can take this colimit and plug in this into the definition of the geometric realization. And so the geometric realization of the simplicial set X, well, I can write this as the general colimit over the category of the elements of the simplicial set X. And here I have the standard simplex delta n tensor product with functor delta top, right? And then I can notice the general formula. So if I have a tensor product of a representable functor, so contravariate representable functor, h to the x, there's some other functor. Well, quite generally over some category D, and this is in this case, this V is just sets. But you can generalize this to the enriched context. So this is isomorphic to the F on the X. And this statement is called the Koyoneda lemma. So if you take the simple tensor product, you just get the evaluation of functor F at the X. And how you can prove this? Well, there are many ways to prove this. Probably the most elegant way is to notice that you can interpret tensor products as the left Kahn extensions, take left Kahn extension log the functor identity and get this formula. But you can also prove this directly. You can take this as a definition and kind of just plug in the Hx into this definition and do the computation. It also, well, it's a little bit longer, but it also works. So leaving this as an exercise. But if I, and also it's kind of written in any reasonable textbook on category theory. So if I now use this, right, so since this delta is a representable functor, so to finish this computation, I need to take this delta top and compute this on the n, right? But this will be just the standard topological simplex. So the answer for the geometric realization, another one, that this is colimit of the delta n top, and a colimit is taken over the category of elements of the simplicial set X. So the X itself is the colimit of the standard simplices, and the geometric realization is the same colimit of the same diagram but over topological simplices. I think that's kind of nice formula, and also in some cases you can take this as a definition. Okay, so and I think that maybe it will be reasonable to continue this general category stuff and introduce the notion of what is now called in the literature. So let me say that this is digression. So through the category theory, this is the nerve realization context. So this situation that we have with the geometric realization, it could be generalized into many, many different situations. And we consider here, just to be a little bit more general, we say that C is a small category. Right, you can, in our computations, this C is delta. So then I want to use short notation per C. This will be just all the functors, so the category of functors from the C op to the sets, and this per stands for the pre-sheaves on the category C, which is by definition just this category. And also I want to fix some E. This will be a co-complete category. Right, because I will continue to do some computations with tensor products, I need them to exist, so this is co-complete. And also I fix some functor, let me call this Q, but probably this is not the best notation. So this is just a functor. So we have this data, like for example, in our case, the C is delta, this per C will be the simplicial sets, E in this case will be the category of topological spaces, and the Q will be delta top. So, but you can generally take this data and define two functors. I can define Q with a lower Schrick, and this will be defined, so let's say on something blank, this is defined as the tensor product over C with the functor Q. And also I can define the functor which I'm going to call Q with the upper star. This will be from the category, yes, this is for the from the category E to the pre-sheaves. Well, and this is in the other direction, right? So here, maybe I need to write this. So Q with a lower Schrick as a functor, well, it it takes a pre-sheaf, right? So this is from the pre-sheaves on C. And when I do the computation, I'll get something in the E, right? Because the tensor product is just an object in the category E in this case. And as you can probably guess, well, I haven't write the formula. Well, maybe to have the same notation, symmetric notation, I'll write this as the lower formula, and here I write the formula. So the Q with the upper star is defined by the following. So since this is functor on the E, if I want to write the formula, I'm computing this on the object, and this will be just the composition of two functors. So one of them is, again, the main representable functor. So this is contravariant represented by the object little e, with composition with the Q. Right?
So, sorry, why we have pre-sheaves in sets, not in E? Maybe.
No, I'm just telling you what happens if you consider pre-sheaves in sets. So you can generalize this. You can replace this sets by, say, any symmetric monoidal category. It is possible. E is something like topological spaces in what we've considered before. So I just want to say that this computation, this particular definition and its properties actually comes from one general scheme that works in very general situation. And I'm going to give you several examples, which are relevant to the course, but not necessarily. Yeah, if you're interested, yeah, in this case, this is what I call the tensor product. This will be from the set cross what I call E to the E.
Just constitution product.
Well, this is what's called the copower. So this tensor product, well, I need to write, maybe I just use another blackboard. Yeah, I think that's important comment anyway. Maybe I just continue to use it here. So the tensor product in this case so as I wrote tensor product, this is from the sets cross E to the E. And if you, there's also a notation for this, different from the tensor product. If you have a set, so S is a set, little e is an object in this category of large E, so then S tensor E, this is another notation for this. If you use special case when this V is just a category of sets, notation is just S dot E. And this is defined as the coproduct over S. So just a standard fact saying that if you have a locally small category, it is enriched over sets and tensored over sets with this tensor product. Okay, so of course, maybe I formulate it here. So of course, as follows from the notation, I expect that these two functors that I just defined are adjoint. Right, so Q lower shriek is left adjoint to the Q upper star.
So this coproduct is over a diagram that has no morphisms. It's only points.
Yeah, this is all overset. Yes. Yes. Okay, so this is for this pair of functors. This is the main property. And is that blackboard visible? Okay. So, and how we can prove this in this general situation? Well, it's again based on the Coyonet dilemma, right? So I know that since I work with the presheaves, I take X now to be this general presheaf, over some category C, I know that I can write this as the colimit of some representable precious, right? So then I have still the co-unit dilemma. So in this case, maybe just formulate this one more time. So the tensor product of the hx over c with this functor q is precisely q computed on x. So these two observations allow me to prove, well, the following proposition, which is the straightforward generalization of this proposition, of this kind of observation. So proposition says that whenever I consider the tensor product of the x and q over c, this will be isomorphic to the colimit over the category of elements of x over the q that I compute on the x. So this follows from this bullet and this bullet immediately, right? I just take this colimit, plug in this into the tensor product, commute this, and use the co-unit dilemma to get this result. Okay, so this allows me to prove this injunction. Right, the computation is simple. And for shortness of the notation, instead of writing homes, I'm just going to use the name of the category. So I'm computing the home in the category E from the tensor product to some object little e. So first thing, I just plug in the colimit formula that we just derived. So colimit of the q of x, this is all the x in the category of elements of large x e, right? Since this is colimit in the first argument, I can pull it out and write a limit. So this is a limit over the same category of elements e q of x to the e, right? And actually, we almost finished, right? Because the next observation is, well, yeah, the next observation is that I keep the limit, but I change this, rewrite formally this home as the natural transformations from the hx q upper star of e. Right, so that's probably the only non-trivial step that we have. Well, to explain this, well, this is definitely Ioannidis lemma, right? Ioannidis lemma, if you compute the natural transformation from representable functor, well, what will you get? Well, you'll get, well, this is a pre-sheaf, right? So this thing, by Ioannidis lemma, we think about this as the q upper star, which I compute on E. So this thing is a pre-sheaf, and I can compute this again on X, right? And when I do this, I'll get a set X. But what will be the set X in this case? Well, since I have this definition, right? So this is, I can rewrite this as the E Q of something, little e, right? That's the same thing. But that's just exactly this formula, which so that this formula is the same as this formula, it's just definition evaluated to the point x. Какое e? Потому что хома, если у вас здесь стоит копредел, он выносится как предел в любой категории. Как бы это контовариантный функтор. Ну, представимые функторы коммутируют с пределами, но здесь сложная категория, поэтому здесь копредел. Потому что я хочу доказать сопряженность, и у меня после, начиная я здесь с хома в категории Е, а закончить я должен хомом в категории предпучков. А хом в категории предпучков — это натуральное, естественное преобразование. Потому что предпучки — это просто функторы. Okay. So this step that looks like a non-trivial step is actually just plugging in the definition of the functor q upper star. And now I can just finish my computation if you just take this limit outside and put it back as a colimit inside. So I'll get natural transformations. So here I have again colimit hx q upper star of E, which is natural transformations from the x to the q upper star. Okay, so that's the proof of this injection, which quite general, works for any presheaves and any category E. Okay. So, since we have this general situation with these two functors, we can consider an example. So, in the case, so maybe I just organize, well, okay, yeah, maybe this is a list of examples of this general situation. So, first example, C is delta, E is top, Q is delta top, right? So then the functor that I called Q lower Schrick is by definition the geometric realization, and we know that there is a functor Q upper star which is called the functor S, and this is, so S is a functor from the topological spaces to the simplicial sets, and this is called the singular simplicial set of the topological space X. And we automatically get the adjunction, right? So the adjunction looks like this. So if you have, let's say, topological space X and topological, simplicial set X and topological set Y, then this is the same as the Holman simplicial sets from the X to the S of Y. Well, the functor S is defined like this Q upper star. I can take this definition and rewrite this definition in this particular case. So the S on the X, just don't want to do mistakes. So where is it? Yeah, so if you look at this as a simplicial set, you can write this for the n simplices. This will be just a home in the, well, I'm writing top. So home in the topological spaces from this topological n simplex to the X, right? This is for the kind objects, and the simplicial operator is acting here, so get this as a simplicial set. And that's, as you can see, the standard definition from the topology, right? Because, for example, what sits in the degree 1? Well, this will be just the path in the X, right? So if in degree 2, this will be a triangle in the X. So continuous map from the one simplex to the X, continuous map from the triangle to the X. So this is indeed, I think in the standard topology course is usually called indeed the singular simplicial set of X. This is how you define simplicial homology and cohomology, right? You take this simplicial set, you construct a free simplicial group on this set, you use Dort-Kahn equivalence to get a chain complex, you compute homology of this chain complex. This is called the singular homology of X. So this is standard thing from the topology.
I have a question about the middle word.
Sure.
So there you write xn times this middle small word on the top. Xn middle small word on the top. Yeah.
Mm-hmm.
Xn times delta n top.
Mm-hmm.
By times, you mean just usual Cartesian product, or you mean also the push out? So there xn is a set, delta n top is a topological space.
Yeah, I said you can interpret this in two ways. Or you can think that you take as many copies as you have points in the X, or you can say that on the xn you have a discrete topology, and take a product in topological spaces.
Okay.
And also this will be what I defined here. Okay, So this was our first example, the computation that we, well, not the computation, but the situation that we consider for geometric realization. And actually, there are many more situations, and this is the reason why I do this digression. We have this pair of adjoint functors. So in the second example, this will be what we will study maybe next time. So as the category C, you still take delta, but now as a category E, you take the category cat of small categories. Now functor Q, I just write the formula for this functor. Well, it's kind of tautological, right? So since this n in brackets, we think about this as this ordered set, right? This poset, actually totally ordered set, but not important. With any such partially ordered set, we can associate a category, right? So the objects here is 0, 1, etc., and there is only one map, let's say from the 0 to 1, from 1 to 2, etc. So this is a category associated to any poset. And just to distinguish these two objects, I write this different notation, but usually people don't do this. They just write this for the partially ordered set, and the same symbol for the category. So we can interpret this and in parentheses as a category. So then the Q lower star is the homotopy category of a simplicial set, and the Q upper star, so Q lower shriek is the homotopy category, Q upper star is what is called the nerve of a category. And the nerves we will study in more details later, but general definition just comes from this nerve realization context. And now we can see why this is called nerve realization, because these two most important examples, you get the realization and the nerve. So example number 3, I just want to mention that probably I won't have time to discuss, to use it in my course. So the homotopy coherent nerve. So this is a situation where you consider, well, E is cat delta. So this is simplicially enriched categories. So meaning that you can define on the homes not just the structure of a set, but so of simplicial set. So home, oh, maybe let me write, if I have something like, what would be a good name? T. You have T here, right? And I compute something like Txy. This will be a simplicial set. And all the axioms are, also, for example, the composition is just a map of simplicial sets, etc. So these are simplically enriched categories. And then for the simplically enriched categories, you can also do this construction and get the generalization of the notion of a nerve. So here, functor Q, the most important functor from the delta to the simplically enriched categories, defined as follows. So say Q, which I apply to the n, has objects 0, 1, etc. up to n. And if I want to understand, so say home, again I'm writing short notation for the home, this is home, space between I and J. So this is by definition the nerve of some poset, which I'm going to call Pij. So the nerve here is the same nerve that I've defined in example 2. So this one. So and this Pij is a poset or automatically a category. So Pij is the poset of subsets I and j that contains, so the interval I and j that contains I and j, right? So this will be a partially ordered set. You can think about this as a category. You can take the nerve of this category, and also you can think about these subsets as the path, right? And then the composition is induced by the concatenation of the path. So this is how we get the category, compute the nerve, and this is the home space in this category. So in this case, Q upper star from the simplicially enriched categories to the simplicial sets, this is called the homotopy coherent nerve. And functor Q lower Schrick from simplicial sets to the simplicial categories. This is called the rigidification of infinity categories. Oh, but you can rigidify any simplicial set, but infinity category is a special kind of simplicial set, so you can restrict this to the infinity categories and get the functor of the rigidification. But not important at the moment. It's just a name for this because it's usually applied to the infinity categories, not arbitrary simplicial set. Okay, so this is another example of this situation. Maybe one more simple example, the Daskin nerve. Well, this is very simple generalization of the usual nerve. You take Q in this case to be mapped from the delta to the categories. This is as before, as an example number 2, so namely this one. Then you take categories and you can embed this in the bicategories, right, in the same way as you can embed sets in the categories. So bicategories are just categories enriched over categories, like the bicategory of the small categories. So then in this case, Q upper star, it has notation also ND, D for Daskin, so this is functor from the bicategories to the simplicial sets, and this is called the Daskin nerve. So I'm not going to repeat this. So this is the Daskin nerve.
Yes, so by category means something like two category.
Two categories usually assumed to be strict. This is not strict. So this is why I say by category. But you can also consider a strict version. It also works.
So by category you mean that it's category where home sets are categories?
Yes.
All categories.
Yes. But you can relax instead of writing some formulas that something is just equal, you just say that there is just isomorphic. So this is kind of, you can define a strict n category as the category enriched in the n-1 categories. But you can also kind of explicitly write all the coherent diagrams and relax some conditions from the identities to the isomorphisms. And this is called bicategories for the, or instead of two categories, say three categories instead of the categories. Well, I mean, you write this using letters, not numbers. Okay, so that's the Daskin nerve, and as you can see, you can continue doing this game, right? So instead of the simplically enriched, you can, for example, take the DG enriched categories. You can take A infinity enriched categories. In all the cases, you get the construction of the nerve. And another example of this pair of adjoint functors will be something like this. You take, you consider enriched situation, and you take C again delta, but instead of the pre-shifts and sets, for example, you consider pre-shifts in abelian groups. So then you get the category of simplicial abelian groups. And the other category, it will be the category of the chain complexes. Again, you get two functors by this construction, and these two functors that realize a dot count equivalence. So that will be another example of this no-ferrization context. And the general idea is the following, right? So you have, for example, something like this huge category of simplicial sets. Inside this category of simplicial sets, well, you have the category which I'm going to call maybe QCat, quasi-categories, just special kind of simplicial sets. And then there is the, say, there is the categories, then there is a NORF construction that give you something here, right? So this will be, categories will be inside quasi-categories. Then you'll get something like, for example, DG categories. You'll get the DG NORF, and you still get something, well, potentially maybe with some intersection, etc. So all these categories in which you kind of can do just general category theory or some enriched category theory in the direction of the homotopy enriched category theory by the construction of the NORF. So this is NORF, this is DG version of the NORF. Then we can have something like the categories enriched over simplicial sets, and you still get somewhere here. All these constructions give you something inside the quasi-categories, and so kinda you, yeah, and this, for example, this is fully faithful. So the categories are still here. You can do the standard category theory here, but you can also kinda, the idea of this this whole part of the mathematics is that you can take the standard approaches and results from the category theory and kind of extend this from this small set to the whole set of the quasi-categories. And this automatically gives you the computations not just for the categories, but also for DG categories, infinity categories, simplicial categories, etc. So this is the end of this digression about the NORF, what's called the NORF realization context. And now we continue our discussion of the geometric realizations. So we can discuss something more interesting. It doesn't follow immediately from the category theory. Or, for example, the following theorem, which is due to Milner from 57. So if X is a simplicial set, then the geometric realization, so then is the CW complex with one n cell for each non-degenerate NG for shortness, non-degenerate n simplex of X. Okay. So the proof is based on three very simple observations. The first one is that if you take geometric realization of the standard simplex, well, you'll just get the standard topological simplex, which immediately follows from the definition. Right, so then there is a small computation, which I'm leaving to you as an exercise. Right, if you take geometric realization of the boundary of the standard simplex, well, you get the boundary of the topological simplex, namely this n-1 dimensional sphere. And I can even write the precise formula for this. This will be the points x0 up to xn in the standard topological simplex, satisfying the condition that there is number k among these indices such that x with this index k is equal to 0. So, simple observations. And then the next simple observation is that, well, since I know that this is a left adjoint to the simplicial, singular simplicial set of some topological space, I can say that this thing preserves colimits. So, and then I'll get the following push out, which I'll get by looking at the skeletal fibration and applying the geometric realization. And geometric realization preserves colimits, so it preserves push-outs. Right, so X is the union of the realizations of the skeletons of the X. So the claim of the theorem immediately follows from this observation that this preserves push-outs. Okay.
Direct limit.
Here?
Yeah.
Yeah, this is direct. This is just a union.
Yeah, but you just didn't write стрелочку, вы как-то не вставили
А.
просто черточку, и поэтому ага, и...
Okay, so this is one property of geometric realization, and another property this we should. Ah, yeah, thank you. Yes. So you can see that this property is quite simple, follows from the general theory, and there is another property that's not so simple. It requires some interesting proof. So next goal, so what I want to show, and won't be immediate, is to show that the geometric realization preserves finite products. Right? This is not a trivial statement, and we will see actually the way I formulated this is not even a correct statement. We need to modify this a little bit. Well, I need to introduce one more category, just briefly. So definition, it's the category of intervals. I'm going to denote this int has totally ordered sets with top and bottom elements as objects and morphisms are monotone maps preserving top and bottom. Okay, I need this category for some technical step in the proof of this goal. Okay, so about, yeah, and also let me immediately say that what I'm going to call fint, f-int, this is a full subcategory of finite intervals, finite as sets.
Can you explain this definition? So like, we have category of intervals and we explain what objects and morphisms.
Yes.
Yeah.
Yes.
And so like these intervals, it's intervals in what? In
They're not in something. This is just abstract, totally ordered sets, where I fix the minimum and the maximum, the top and the bottom. It's usually called in this theory. Like for example, in the fint, you get exactly the same objects as you get in the delta, as you can see, because this is finite intervals. But in the int, you have all other intervals. For example, have the standard interval between 0 and 1. That's also object and int. Right. You'll see how this is related to the delta and why this is relevant in several minutes. So the first observation why this is relevant is the following lemma, which I'm going to prove, which I'm going to leave as an exercise since this is quite easy. So this find is actually equivalent as a category, just the opposite of the delta. And this equivalence, well, maybe you can consider this as a hint. The equivalence that realizes this is just the home, say going in the other direction, home in the category delta, well, from something to the 2. So you can notice that if you look at this functor from the delta to the find, you'll get exactly the equivalence of categories. Okay. So next, I want to look at the following lemma, and says that the square is commutative. So the following square is commutative. So here I have delta, which I identify with the find opposite. Right, so then there is functor delta top from the delta to the topological spaces. So then there is functor u, which is just the forgetful functor. So you associate with the topological space the set of points. So usually this is called u. And then here for the find, you can include this into the category of all intervals, right? And then here are the functor that I consider is the home in the category int to the I. So let me say that u is the forgetful functor. And this I that I have here and at the bottom of the diagram, this is just the standard interval 0, 1. Mm-hmm. This is op. Thank you. It's just, you can see this is op because this is contravariant functor, obviously. So why we need this? Well, because I want to understand in my proof that this preserves finite products, I want first to show that the underlying sets are bijections. So that the composition of this geometric realization and the functor u preserves finite products. And then kind of from this, it's quite easy to do the proof for topological spaces. So this is kind of the key step. And to do this, I want to understand this composition, and I understand this composition as this composition. Okay, so the proof is just a simple computation. Well, kind of I'm leaving everything to you to do with the arrows, but I will do the computation for the objects, right? For example, if I take n here, I understand what happens. So this n is sent to the standard simplex, and this will be the just the points, right? The set of points in the standard simplex. I want to understand that when I do this computation, I'll get the same. So let me say, you can notice that, well, if you take n minus 1, it will be convenient for me to work with n minus 1, right? So this is first, this lives here. I first go to these finite intervals. So this goes to the int n minus 1, n minus 1, home into 2. So what is this interval? Very simple combinatorial question. Well, what's the cardinality of this set? No. Нет. Well, what is this interval? We consider all the maps from this interval to the interval which has, well, just 0, 1, and 2. This is 2. 2. Well, because this is the functor, well, I'm going to here, from here to here first, and I need to apply this functor, which gives me the equivalence.
the intervals or in the delta or?
No, this is in the intervals, right? No, no, sorry, just no. This is not. This is, you're right. This is in the delta,
Ah.
right? This is in the delta, right? Because I'm starting with n minus 1 here, going to the finite intervals. So this is this functor.
So how many was there?
Again, it's not n plus, it's not n.
It's n plus 1 actually. So do this combinatorial exercise, but this has to be n plus 1, right? So this will be this interval that lives here. So then I consider this as just an interval in this large category and apply the last function. So and then this will be the home in the category of intervals from the n plus 1 to the I. But now, as a set, of course, you can notice this is precisely the points x0 up to xn.
This is a unit interval in R, or if this is just 2 points?
No, this is kind of as a subset of R. Yes. Okay, now I'm confused about this. Is this n plus 1 or just n?
N,
Yeah, I think this.
it consists of n plus 1 elements, but it is n.
Yes. Yeah, I think that's right. Yes. Yes. Yeah. So now here this will be this n plus 1 points, which are just points in this interval. So this is I to the n plus 1, right? And the condition, since this is just not any map but a monotone map, is the following: that the x0 is x0. This is less or equal than x1, etc., until you get xn minus 1, which is less or equal than xn, which is 1, right? So this is just an explicit computation, what you'll get if you go in these two directions. But of course you can see that this is precisely the standard simplex. Right, so this is u of the delta n top, right? You can, for example, take the differences, x1 minus x0, x2 minus x1, etc., and this will be the points such that their sum is equal to 1. It's kind of one of the ways to parameterize this standard simplex. So this is, for objects, this is the end, and this we have this lemma. Well, maybe this is n minus 1. Okay. So the next lemma, so with two parts. The first part is kind of trivial, doesn't require a proof. Any interval is a filtered colimit of finite intervals. And part 2, so take some interval j, then a condition that this j preserves filtered colimits. No, this is, let me write int. So this will be. So when j preserves the filtered colimits, well, in the abelian categories, this is called finitely presented objects. In triangulated categories, this is compact objects.
J is from F int.
From int. So I'm looking for which intervals has the property that they commute with the filtered colimits. Да, я его вынес, конечно. this is holds if and only if this J is infinite. So this finite intervals is something like finitely presented objects in this category. Well, it requires a proof, but since the category is kind of explicitly given and so it's easy to understand, I leave this as an exercise. The first part is trivial. This requires some proof. It's not trivial. But what's an interesting corollary for me is that if I look at the functor, which is the home in the category int to this I, and restrict this to the finite intervals, right? Since I know that this I, in particular, as any interval, is a filtered colimit, and this home will commute with the filtered colimit, right? So I can say that this functor is a filtered colimit of finite intervals, of representable functors represented by finite intervals. Okay, so the proposition is that the composition of the U with geometric realization preserves finite limits. Okay, so if I look at this composition, so I compute the functor U on some geometric realization of a topological space, well, since I can write this as the tensor product with the delta top over delta, and now since this is some colimit and U, well, this forgetful functor from topological spaces to the sets, it has left adjoint, has right adjoint, right? So it preserves everything, limits and colimits. So in particular, it preserves colimits. And I can write this as a tensor product of X over delta with the composition of the U and delta top. Now, this composition of U and delta top by the lemma that we computed here is the same as just this kind of after this embedding the functor into the I, which is a filtered colimit. So I have this is X tensor product over delta with some filtered colimit of representables. I'm going to call this HK. So tensor product commutes with colimits. So this is filtered colimit. So Koyana dilemma. So this is the answer, right? And now, can you tell me why it's clear from that answer for this composition that this preserves finite limits? Well, because filtered colimits commute with finite limits. And let's give me the proof. So I see that I don't know yet the geometric realization preserves products. Actually, it also preserves finite limits, but I know that this with composition with the forgetful functor preserves products. Now to extend this, U композиция дельта топ. Right? Now, to drop this U in this composition and just get the property of the geometric realization, I need to notice one thing. I need to notice that we need to modify the category, usual category of topological spaces, since top is not Cartesian closed. closed. So there is no right, so there is a Cartesian product, and you want to have the left adjoint to this Cartesian product that you want to call the internal home, right? And just in the category top, there is no such good notion. But you can instead consider category, so we consider what is called K-top. There are many other versions. For example, you can consider compactly generated, but this is kind of the minimal thing that you need to do to improve the situation.
We want to prove that this recommendation preserves finite limits. That's our
Yes.
immediate goal.
Yes.
And we cannot just use the fact that U preserves all limits and U is strict.
Oh.
In the conventional map from the
But
recommendation of the limit to the actual limit, and when we apply U, it becomes isomorphism, right?
Yeah, you get it just the bijection. So the moment we can get bijection of spaces.
Yes.
So we consider the category K-top. So how this is called? Well, this is called the category of K-spaces. I think this is the right name. So how it is defined? So first of all, I can say for the subset, so A in X is compactly closed. Just doing some general topology now. If for any map F from K to the X, where K is compact Hausdorff, C Haus for shortness. So this is compact Hausdorff. So the pre-image F inverse of A is compact, sorry, is closed. So this is compactly closed subset in X. So a definition, a topological space X is called K space if every compactly closed is closed. If any compactly closed subset is closed. So you consider a full subcategory, K-top inside all topological spaces, and this inclusion has the right adjoint. This is called K, and this is K-ification. K-ification of a topological space. So this K-top is again complete and co-complete, but now this is Cartesian closed. No, you can verify this or look into any textbook on general topology. Cartesian closed means that this is kind of notion from the monoidal category theory. You have a monoidal product which is just a Cartesian product. And Cartesian product means that this monoidal product is closed, meaning that there is a adjoint functor which is the internal home.
Можно спросить, а правда, что K-space это будет что-то типа просто пополнение фильтрованного пределами из хаоса?
Я не уверен, что это верно, но на 100% не знаю. Well, anyway, that's the definition that I'm going to use. So the point is that in the top, when you consider, well, what we need, when you consider product in top, right? This doesn't commute with the colimits in both variables, but the product in the K-top commutes. Well, and the product, well, how you compute, for example, not just products, but any limits here. You compute the limit here, and then K-ify this limit. And of course, for the colimits, you just can compute colimit here, and it's already will be here. Okay. So now I have the proposition. Maybe I need to formulate this, maybe this theorem without proof, to emphasize that this is important. So K-top is Cartesian closed, which is not true for the top. This is statement from general topology, which I'm not going to prove. What I want to prove and to finish today's lecture is the following. So the geometric realization from the simplicial sets to the K-top preserves Well, I do the finite products, and as an exercise, you can do the binary equalizers. Preserves finite products. Well, let's consider just three simple steps. So step one. Now we are ready to give a very simple proof of this statement. So step one, if I take the geometric realization of the delta m cross delta n, I take a product of two standard simplices and take a geometric realization. So this is compact. Why this is compact? Yeah, that's exactly right? Because you have only finitely many non-degenerate simplices in this product, right? And then the geometric realization is CW complex with finitely many cells. So that's compact. So that's a simple observation. Now, step two, which is just another observation from general topology. So the canonical map from the geometric realization of the product of standard simplices to the product of geometric realizations is a homeomorphism. Well, we know that this is, so we know this is bijective by our previous consideration of the composition of the realization and U. We know that domain is compact Hausdorff, and well, codomain is also compact Hausdorff, right? So domain and codomain, they are both compact Hausdorff. So by the general theorem, if you have a map of compact Hausdorff spaces, which is bijective, then this is continuous map, and then this is homeomorphism. So that's the end of the proof of step two. And finally, step three, if I have a general geometric realization of two simplicial sets, well, I write this as the colimit over elements of X for the first factor, colimit for the second factor over the elements of Y, right? Geometric realization commutes with colimits. I can write this, say, as a colimit over the product of elements of X, product elements of Y, geometric realization of the delta n cross delta m, right? So then this will be still the same colimit, geometric realization of delta n product. Now, since to indicate that this is in the k top, not in the k, I write for this product index k, right? Because the product in this category, you compute product of topological spaces and then apply this kification, the right adjoint functor. But, well, really this is just to emphasize why this is important. Well, because actually, of course, for these nice topological spaces, this k phi product is the same as a standard product. Well, maybe actually. Well, I just since now I work in the.
Yeah, I mean it's not X, it's this. X times X plus Y equals colimit of X. You're right, but it's not X.
No, this is over elements of X across L.
The whole line.
Wait, what?
You're right. X equals colimit of X.
Ah, yeah. So yeah. Yes, thank you. Colimit of the delta n. And this is colimit of the delta m. Yes, thank you. So this is still colimit of the elements of X product with the elements of Y, right? But now This is why I used K top instead of the top. This will be, since this commutes now with colimits, this will be colimit of the realization of the delta n, colimit of realization of the delta m, and this will be just the x. Yeah, so now this is important. I can write this k everywhere, but this is coincide with the standard product in topological spaces. So this is the proof that you can commute geometric realization with finite products. As you can see, this is not a automatic property that follows from category theory. You need to do some computation. Well, to say that you have this closed structure, it means that this product, right, so the product with the k, it commutes with colimits in both arguments. For this, you need k top. This is not true in top. And what you can prove, for example, if you don't, for example, like to work in the k top, you can work still in the topological spaces, but you need to do some additional assumptions to get this property, right? You need to assume, for example, that this is a CW complex and this is CW complex. And as we all know, the product of CW complexes is not necessarily CW complex. There was an example of Docker in 1952. So, but if you assume that this is CW complex, then this is still true. But the proof is a little bit more complicated. And of course, K-top is not the only version that you can use instead of top. You can use, for example, compactly generated topological spaces, maybe some other topological spaces. Well, you just need this to be, well, to include topological spaces that you need for your applications, and also to be to have this property, this product can use with colimits. In other words, this is Cartesianly closed. Okay, let's stop here.
Could we approach step 2 geometric, or it is complicated?
Просто построив всякое разбиение?
Ну, да.
Несомненно, да, конечно, можно, да. Мне кажется, я где-то видел, как это было сделано, там, типа, Гельфанд-Манин, может быть.
Мы еще не доказали, что гиперсериализация функционирует с конечным пределом.
Мы доказали с конечными произведениями. И это все, что я вам обещал, потому что уравнители я оставляю уравнением.
Можно пример ставить еще один? То есть у нас шапка раз это, потому что каждый компактный замкнутый